I am Hakeem Oluseyi. I am an astrophysicist and author of the new book, Why Do We Exist? The 9 Realms of the Universe That Make You Possible.
The 2 multiverses we might live in.
What do physicists mean when they say a multiverse? It is derived from what we mean when we say a universe. And a universe has characteristics. And one characteristic is sort of like defining a living cell, right? The thing that defines a living cell is that it contains a volume that encloses it and separates it from the rest of existence. So a universe is that. It's a volume separate from the rest of other existences. And inside that universe, there are specific physical constants that characterize the physics within that universe and the interactions within that universe. Things like the gravitational constant, the action constants that we call Planck's constant, or the constant that combines energy and temperature that we call the Boltzmann constant, right? Then there are some other more obscure constants in there, like the fine structure constant. But these constants, these values, we don't derive them. They just are, right? And so every universe will have its own set of constants that define how physics takes place within that universe, and it will be a volume cut off from the rest of other such volumes. What is the problem that the many worlds interpretation of quantum mechanics is trying to solve? It's trying to solve what we call the measurement problem. And the idea that, when we make a quantum measurement, that vector that describes the state of the system goes from being expressed as a sum of the possible states of the system, right? When it's measured, it will only be found in one state. But in the pre-measurement state of the state, we describe it as being a combination of all the possible states. But once you make a measurement, it's always found to be only in one of the possible states. So what's going on there? In the first instance, in the initial state, you have a state vector that's made up of all these sums. And then after measurement, the state vector just ends up having one component of that sum. So what does that transition look like? Well, is the measurement changing the state of the system in this way? And some physicists, what they call the Copenhagen interpretation, say, yeah, the system collapses into that one state upon measuring. But some other physicists came up with a different idea. And they said what's happening here is that every state actually exists. And every state kind of corresponds to its own universe. So the measurement that you get tells you which universe you're in, right? So all of the possibilities, all of the possible states occur at every measurement, but they just occur in different universes, which means that there are different copies of everything in our universe. Every time a measurement is made, you're popping off these new universes. It's weird. It's very, very weird and strange. It seems counterintuitive. It seems to go against conservation of energy. And the other thing is, we don't even really define what it means to make a measurement, right? Is it just an interaction? So for example, if I have a photon and an electron interacting, right? An X-ray that is traveling towards some atom. That atom has an electron. So there's a famous experiment in physics known as the Compton scattering experiment. And this is the experiment that shows a particle property of light, that it exchanges momentum the way particles do, like billiard balls colliding. So in that interaction, before the interaction, both the electron and the light are described as waves, but in the interaction, they both behave as particles, right? So does that interaction create a new universe where each goes from a superposition state into a definite state? So think about that. Many galaxy clusters are full of this hot X-ray emitting gas. And all these galaxies, which contain gazillions upon unfathomable numbers of electrons, are orbiting within that hot million-degree gas. They're being bombarded by X-rays. Is every interaction spinning off a universe, right? It's nuts. And even then, when you talk about the fact that that state vector in the pre-measurement state that wave function, the pre-measurement state, has probabilities built within it, what does the probability of a measurement even mean if every measurement has a probability of 1, right? Every measurement has a probability of certain in some universe. So what do these probabilities even mean? Some people think, on the fringes that might be real. And some, because they think that idea of the wave function collapsing is too unphysical. So there must be some other explanation. And this is one of those interpretations. And I find both explanations to be, okay, I think we're missing something. I think there's something going on that we're not quite interpreting right. We're not understanding right. And, I love to live in mystery. I love ignorance, right? Once you know you're ignorant, you can fix it. you can, it's a provocation. You can design an experiment. You can design a thought experiment. You can design mathematics to get to the bottom of it. And I think that this problem has young, curious people and old, curious people doing exactly that. But if you accept one or the other, you think you got it solved. Now, suppose, we can speculate. The thing about having a human mind is you can imagine things that have never been observed, that, may never be observed, can maybe never exist. But you can imagine it. You can imagine a universe in which the many worlds interpretation holds up to some sort of experimental scrutiny. And we're like, oh my goodness, it's real. What does that mean for our reality? Does that mean that now we have the possibility of accessing those other universes? Well, what you find that happens is a new sort of insight into nature is kind of like a new technology, right? The internet created a whole new economy. Then smartphones on top of the internet created a whole new economy. So whenever you have these new ideas like string theory, right? It didn't work out for physics, but mathematically, it created whole new areas of exploration, right? A very rich area of mathematical understanding and exploration. So the first thing is you don't know what you don't know. So if you find that this multiverse idea of many worlds interpretation turns out to be true, does that mean that we're forever isolated from these other universes and can never access them? That is the current way that most physicists think that, if this were true, that would be the case. But if it turned out to be true, people are really going to start thinking about things differently. And in that exploration, some clever group of researchers may very well find ways of interacting between universes, right? They can come up with experiments that, say, there was once this idea that gravity is so much weaker than all the other forces because it leaks out into this parallel universe. And what we see as dark matter in our universe is a gravitational pull of matter in a nearby parallel universe. And they came with an experimental idea. Well, if you can measure gravity at a short enough distance, then what would happen is you'll see suddenly this increase because that's before it has leaked out into the other parallel universe. It was never measured, but the point is that they came up with a way to measure it. And I think that if we do evolve to a state of finding that, there's something to this, we're not going to stop there. We're going to keep exploring, and who knows where that's going to lead. Another way physics invokes the idea of multiverse is in cosmology. And this came about via a mechanism that was hypothesized to solve a couple of problems in cosmology that researchers began to notice in the late 20th century. And those problems are called the flatness problem and the horizon problem. And the solution is something called inflation. And inflation is this notion that at very, very early time, in the very earliest moments of our universe, the universe doubled in size over and over and over and over again in a tiniest, 10 to the minus some double-digit number of seconds, right? A billionth of a billionth of a billionth of a billionth of a second, something like that. And the consequence of that is that today, regions in the universe that appear that there would have been outside of each other's cosmic event horizon back in those times and could have never communicated with each other, could have never exchanged energy with each other. When we observe those regions today, they appear to have the same temperature, as if they were in contact, right? So if I look at the cosmic microwave background radiation coming from that direction and compare it to the radiation coming from that direction, it's roughly indicative of the universe being at the same temperature. How could that possibly be? That should only, if you do the calculation, assuming a standard hot Big Bang model, it's only about twice the size of the full moon regions that should have about the same temperature, right? But, it's the same temperature across the entire sky. What that means is regions of the universe that today appear as if they were forever outside of each other's horizons were at one point within each other's horizons, and that rapid expansion of the universe took them so far away that they have that appearance today. So what do I mean by horizon, right? So in relativity, every future possibility is bounded by the speed of light, all right? So if you move at the speed of light, there's what you can reach, and you can't reach anything beyond that, right? So you have what is known as a future light cone. So if you look at the future light cones of all the regions of the early universe, if we take those regions today and you go backwards, they would appear to be outside of each other's light cones. But clearly they were inside of each other's light cones. And this inflationary event is what allows that to manifest in a physical way. But then you need a reason for it. How could that have happened? When we started studying how that could happen, that led directly to the idea of multiverses being real. In the cosmological realm, the types of universes that exist in the multiverse are fundamentally different than the ones we see in the many worlds interpretation. So what that means is, you can think of it like baking a loaf of bread, right? You bake the loaf of bread, the bread expands. And inside that bread, there are little bubbles of air pockets, right? So every air pocket has its own history, and yet the bread itself has its own history. And every bubble is separate from every other bubble. So they have their own separate histories. So that's similar to what an inflationary universe would create. But the difference is that the main background, the whole loaf, that universe, right? That thing is there, it's expanding super rapidly, it's doing its thing. And when it pops off bubbles, it doesn't pop them off at the same time, right? These bubbles, where they go out of this inflationary state and then nucleate into a new universe, they pop off, right? One happens here. If another one was to happen very near it, because that bigger space is expanding so rapidly, it will be so far away by the time it nucleates out that these bubbles are forever separate from each other. If the multiverse of the cosmological realm that is generated by this process called eternal inflation is true, then there are multiple spacetimes. There is the bulk spacetime, and I don't want to use that word bulk because there was this old model of brains and bulks, right? But truly, there is a bigger spacetime out there. And every universe has its own spacetime with its own history that evolves separately from that bigger space-time once that bigger space-time, births it. The properties in each bubble universe will be slightly different. Each have its own history. Each have its own space-time curvature. I am so impressed with this animal on Earth that we call Homo sapiens, right? Not long ago, you were eating the leftovers of predators on the plains of Africa. At a certain point, you decide you're gonna break rocks and turn them into tools. And you go from that to melting sand and turn it into quantum technology and performing experiments and understanding that we live in a universe that is evolving. And you make measurements of this light left over from the origin of the universe called the cosmic microwave background radiation. And your physics tells you that, hey, it should have fluctuations of every sort. And if this multiverse thing is real, then there should be this thing called a super horizon fluctuation. And you make this careful measurement, you get to the point where you send up the Planck satellite, and there it is, clean as day, the signal of the super horizon fluctuations. And you say, wow, eternal inflation looks like it's real and looks like we are in a universe. So we have reached the point of experimental verification of the multiverse, but that is a big claim. So it is not a conclusive piece of evidence, but it is a strongly circumstantial piece of evidence. Some physicists do say it's conclusive. Some physicists that I respect greatly say that it's, for their thinking, right, is it's conclusive. I'm not convinced that it's conclusive because I don't quite understand it all yet. But I'm working on it in the midst of everything else I'm working on. So, we've reached that experimental point, and, man, what a fascinating place nature and existence is. What we see in physics over and over is that stuff pops out of the equations that leads us to new discoveries, right? Maxwell discovering that light is an electromagnetic wave by manipulating the so-called Maxwell equations. But, more often than not, stuff pops out of the equations that just isn't true. And you got to find some way of saying, oh, here's how we use that, right? It turns out this part of the equation is reality. That part of the equation is just mathematical junk that's left over. At the same time, though, we have people like Albert Einstein that comes around. And he writes down equations for, say, general relativity, and it creates phenomena like black holes and gravitational waves that won't be measurable for decades to come, if not a century to come, right? So there are things that our equations predict that may be just complete nonsense, and there are other things that may be insights into the universe, but we have no way of measuring them now because we just haven't developed to that level of technology yet. What that tells me is we need to take these predictions seriously. And we need to continue to, as a society, fund people to pursue these questions. Because every time we find out some new fundamental nature of reality, it leads to new engineering that allows us to take advantage of this stuff. Research at the edges, research into these avant-garde ideas is the fertile ground for discovery. And that is where we must explore. Don't just dismiss it as that can't be true. The universe has never cared what you think can be true. It is up to us to listen to the universe and ask the universe, hey, universe, what are you? And our observations and our calculations are the way that the universe answers those questions when we ask.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.